Hello all. In today's session we will discuss next topic, neural network hyperparameters. As I already told in the previous session, these hyperparameters are the variables that are set and tuned by a data scientist before training a model. That means these are the variables that are not learned by the model. So let us discuss few hyperparameters. These hyperparameters are categorized into three different categories. First is neural network architecture, and these are the hyperparameters which explain the architecture of a neural network. The second category is learning and optimization. These four are the hyperparameters that describe how a model learns and optimizes. And the third category is regularization techniques to avoid overfitting. And these are the three hyperparameters that explain different regularization techniques. So let us start with the first category of neural network architecture, where we talk about hidden layers, we talk about number of neurons and the type of activation function as well. So whenever you are designing an MLP model or CNN model or any other neural network model, the point what you need to decide is how many hidden layers you need to have in the model, which is called as depth, and the number of neurons in each layer, which is called as width. So you need to make decisions on these two hyperparameters, that is the hidden layers and neurons. It should neither be too complex nor be too simple. You can see a diagram here which shows three different types of data set. A simple data set where a single perceptron is enough to separate the data, a medium complex where 2 or 3 neurons are enough, and a complex data set which requires n number of neurons to separate the data. And the second type of activation function, second hyperparameter is the activation function. We have discussed the different activation functions, and the main goal of activation function is to introduce non-linearity in the neurons, and this will help our model to solve all non-linear problems. So we have discussed three hyperparameters, the number of hidden layers, we have talked about number of neurons also, and the third is activation function. These hyperparameters describe the neural network architecture. The hidden layer will tell the learning capacity of a model. More the number of hidden layers, more is the learning capacity of the model. Thereby the computational complexity also increases. Next, coming to the second category, learning and optimization. So in this category, we have four different hyperparameters that define how our model is learning and optimizing. The first is learning rate and decay schedule. Second is batch size. Third, optimization algorithms, and the number of epochs as the fourth hyperparameter. So let us discuss the first one, learning rate and decay schedule. According to a data scientist called as Bengio, he have given a statement on learning rate as the learning rate is the single most important hyperparameter, and one should always make sure that it has been tuned properly. If there is only time to optimize one hyperparameter, then this is the hyperparameter that is worth tuning. Now, what does this statement emphasize? It emphasizes the critical importance of this learning rate in the optimization process of neural networks. So this learning rate will be decided, which this was used in algorithm called as gradient descent algorithm, which is an optimizing algorithm which takes steps to reach the goal of your minimum error, the best weight at which your error is minimum, and these step sizes will be decided by the hyperparameter called as learning rate. So we have also talked that learning rate should neither be too small nor be too complex. Anyways, we will discuss different approaches to select the optimized learning rate value also. So first let us consider an ideal case where this was my initial position of weight, and taking some learning rate value, I have jumped to the optimal value. Anyways, this is not possible case, but let us consider this case happens when taking some LR value, I have jumped directly from this value to this value. And now taking this LR value where I directly jumped from this point to the minimum point, take this LR value as ideal learning rate value. Taking this ideal learning rate value, we will define three different cases. The first case is if you select a learning rate which is smaller than the ideal learning rate, it takes small steps to reach the goal. And if you take larger learning rate than the ideal learning rate, then it oscillates in a zigzag movement and there might be a possibility of missing the minimum value. And the third case is if it is much larger than the ideal learning rate value, then you can see that it goes farther and farther from the minimum error, and this phenomenon is called as divergence. Plotting these four different conditions, you can see here good learning rate, ideal case, and this graph represents a high learning rate where a constant loss is maintained, and the purple line represents low learning rate. Though it is taking longer time to reach the goal value, there is reduction in the loss here. Whereas the high learning rate, you can see here there is till few epoch values, you have reduction in the loss here, but thereby the loss value is increasing. Now we will talk about systematic approach to find the optimal learning rate. We will take a parameter called as validation loss to find the minimum value of learning rate. You can find that validation loss will be decreasing in a training process. But if the training is completed also, you still find there is reduction in the validation loss. This might be due to epochs, that is less number of epochs, or might be due to less learning rate. So in that case, what do? You either increase the number of epochs in the code or you increase the learning rate value. And second approach, when you find the loss is increasing, you try to decrease the learning rate value. So these are the two approaches to find the optimal value of learning rate in your model. Now let us talk about another parameter called as learning rate decay and adaptive learning. Learning rate is a hyperparameter that you set some value, you perform the training operation, and then evaluate that model. If you find there is the performance is very poor, then you try to backpropagate it, thereby changing the values or updating the values. So in that case, you are not changing the learning rate value till training process. Once the training is complete only, you vary the learning rate. But learning rate decay is another parameter which will change the value of learning rate during the training process only. So this is the first method called as the linear decay, where you can see that in this example, after every fifth epoch, I am reducing the learning rate to 0.5, that is dividing learning rate by 5. So till fifth epoch it was 1, from sixth epoch it got reduced to half, and so on. This is the first type of selecting the learning rate decay value. Hope you have understood the difference. Learning rate till the training process is complete, this will not vary, whereas learning rate decay is varied during the training process only. And the first method is linear decay, where your learning rate is reduced to half after every 5 epochs. And second method is called as the exponential decay. This is exponential decay, the second method of exponential decay. And in this example, you can see that earlier till 8th epoch it is 1, and after 8th epoch got reduced to 0.1. That is, I am multiplying my learning rate with 0.1 after every 8 epochs. And what do you notice here? That is, it is taking too long time to converge. Though it is converging, it is taking time to converge compared to that of the previous linear decay. This is all about the first hyperparameter called as learning rate. Coming to the second hyperparameter which describes the learning of a model is mini batch size. The batch size hyperparameter has a big effect on the resource requirements of training process and speed. Anyways, let us have a recap on the batch gradient descent and stochastic gradient descent. In batch gradient descent, the entire dataset will be used for training. As the dataset is used entirely at a time, it takes longer time to reach the goal value. And coming to stochastic gradient descent, random data points are used to train the model and then evaluated. And you can see here you have a zigzag movement of the model to its minimum value, that is number of oscillations are present in stochastic gradient descent, and the other name for stochastic gradient descent is online learning. We feed the network at a single instance of training data at a time. And this is mini batch, where the entire data set is divided into batches to train the model, and this can be considered as a compromise between stochastic and batch gradient descent. And you can see that there is a reduction in noise compared to that of stochastic gradient descent in mini batch. Now what should be the batch size? To select the batch size, for example, if you have 20,000 data points in your data set, then no need of dividing this data set into batches, because as this data set is very small, you can use the entire data for training the model. But what if the data set is more complex? Then you need to use batch sizes to divide the data set. And the common batch sizes which we use is, you have 64, you have 128 batch size, 256, 512 and 1024. These are the batch sizes which will be used depending upon the data set given. But you need to make sure that when you are deciding the batch size, this batch size should fit in the CPU or GPU memory. Then only you can take higher batch sizes. Now you can see here a figure which gives the relationship between the batch size, computational resources and the number of epochs. You can see here epochs, this is the batch size and computational resources. These are the three graphs on a single figure. Now what are computational resources? These are nothing but the hardwares and the softwares which are required to perform the computation in a neural network, like CPUs, GPUs and TPUs. Epochs are nothing but the iterations, and these are the three different types of optimization algorithms. Talking about the first parameter, computational resources. In stochastic, you can see that the minimum resources are required. For mini batch, moderate resources are required, and for batch, high computational resources, that is many computational resources are required. And as you are moving from stochastic to batch, you can see that the number of data points are increasing. Coming to the epochs, stochastic gradient descent have many epochs, and this is because we are updating the parameters frequently but with some noisy gradient. Coming to mini batch, the moderate epochs are used here because it will balance the noise which is present in stochastic gradient descent, and batch will use few epochs because the updates are stable and smoother, but each epoch in the computation is expensive. So this entire figure, this entire diagram will highlight how choosing the right batch size will affect the overall performance of the model, thereby affecting the speed of convergence. So this is the end. In the next session, we will talk about the next hyperparameter, that is different optimization algorithms, which will define how a model is learning and optimizing. Thank you all.